And we have Michael Larsen from Bloomington, Indiana, who will tell us about counting representations of Fuchsian groups over finite fields.
Thank you very much for the invitation. It's really a pleasure to be here, always. And yeah, so this is one of these stories about counting the same set in two different ways. And in this case, the set is something that looks like this. Gamma, G of Q. And let me explain what everything is. So gamma is going to be a Fuchsian group, which for me means it's co-compact and it's oriented. So it's a group which has a presentation which looks like this. It's X's, Y's, some Z's, and you have some relations. So Z1 to the N1, C2 to the A2, VR to the AR. A1 through AR are just integers greater than or equal to 2. And finally, the relation is the product of the commutators taken in order times the product of the z's taken in order is equal to 1. This is the kind of group that I'm interested in, but there's a condition on the various parameters, which is given in the following way. So we define the Euler characteristic of gamma in the only reasonable way that we could define it. So that means it's 2 minus 2g. So that's the part which doesn't come from torsion, minus relation I equals 1 to r of 1 minus 1 over ai. And this should be less than 0. With this condition, we actually get a Fuchsian group. So gamma will be a co-compact subgroup SL2R. And so that's the gamma that I'm interested in. And G will be, let's say, connected reductive group over finite field. But in fact, in this talk, G will be either SLN or GLN. And so this is what I want to count. And there are two ways that I know to count it.
AI can be infinity also.
That's it?
AI can be infinity.
No. For me, AI is.
I don't understand this notation here. So this is the generators for your.
Yeah, these guys over here, the X's, the Y's, and the Z's are the generators.
Yes.
And the relations are that the Z's are of specified order. I specify what the orders are going to be.
Okay.
And then in addition, if I multiply the commutators of the X's in order, so X1 commutator, Y1, so by Xi, Yi, I mean, right. If I multiply them in order and then I multiply all the Z's in order, I get 1.
You have to multiply all those in order.
All the commutators of the X's and Y's.
And everything.
Everything in order.
And that has to be 1.
And that has to be 1.
Okay.
Okay, so that's the kind of group that,
Yeah.
So that's the kind of group I'm interested in. And then I want to count homomorphisms to either SLN of FQ or GLN of FQ. And the 2 points of view that I think one can reasonably take about this, maybe there are others that I'm not thinking of, is on the one hand, we can think of these things are algebraic groups. So we can think of Hom.
So you say that from this presentation, you deduce that gamma is co-compact?
Yeah, for this presentation, so yeah, it turns out that every co-compact Fuchsian group is of this form, and every group of this form satisfying this inequality is a co-compact Fuchsian group. So it's,
You have to have that inequality.
you have to have this inequality. This, geometrically says it's negatively curved. Right? This is the reasonable way of defining Euler characters. The trouble is, if we didn't have these points of finite order, this would just be the fundamental group of a genus G surface, right? But this is kind of like, instead of looking at a curve, I'm looking at an orbit curve with, quotient singularities. So, so I can think of G just as an algebraic group, and I can think of homomorphisms from gamma to G as a variety. in fact, an affine variety over FQ. And what I want to do is I want to count the points on this variety. So count the points. Or I can say, well, whenever I have homomorphisms from a Fuchsian group to any finite group, right, there's a formula for the number, which I'll write down in a little while, but there's a formula which has nothing to do with the structure of the finite group. It just has to do with the characters of the finite group. And as I said, it's the formula due to Hurwitz, and I'll write it down in a few minutes when I need it. But if we compare these two points of view, then we get something which, depending on your interests, could either tell you something about the geometry, knowing something about character values, or it could tell you about something about character values if you know something about the geometry. You can use it either way. I'm more interested in using information about the character values to tell me things about the geometry. In fact, the character values themselves, via the theory of Lin-Listig, there's a kind of a geometric way of thinking about them. So in fact, we're comparing geometry of two different kinds, but it's kind of like Fourier transform, okay, so that's the story. Now, what am I going to use this for? So there are two applications I want to talk about. One of them I talked about at Nick's birthday conference, and I apologize, I think you're the only overlap in audience member, but the results are a little better now than they were. But in any case, so one of them has.
I was there.
Oh, I thought you missed the talk. I think you missed the talk.
Huh.
I've been looking forward to.
No, I think I didn't.
I think you were there. Okay.
Maybe I was in, but.
All right. Anyway, yeah. So one kind of question that I want to be able to answer is, okay, I mean, if we were to fix n, fix whether we're in SLN or GLN, then we would understand very well what the sort of asymptotics of the growth of this set would be as Q goes to infinity. Because this is a standard kind of problem. You have an n-dimensional variety, you count points over FQ, when Q goes to infinity, you get Q to the n points if it's irreducible. Maybe it has several components, so maybe it's a constant times Q to the n, maybe it's irreducible but not geometric. Like there's a story, and it's not a very mysterious story. So we understand that very well. But what's certainly more mysterious is what happens if we fix Q and we let n go to infinity, right? And so that kind of question we would like to say something about. What are the asymptotics of gamma GLN Q when gamma and Q are fixed, but n goes to infinity? And the guess is that we call this a number, I don't know, let's just call this AN, that AN will be asymptotic to some Cn times Q to the power of 1 minus pi of gamma times n squared, where.
What do you mean by Cn?
Okay. I have to say something about Cn. Where Cn is periodic in n.
So what's going to infinity? Q or n?
Right, so that's the point. Q is fixed, but n is going to infinity.
Okay.
Right. So this is the prediction. And in fact, one hopes for more, that one can actually say something about the structure of Cn. So we want to, so roughly, Cn should be given by a formula like this, Fnq, well, okay, Q is fixed, so I'll just say Fn of 1 over Q, where Fn of Q, this is this terrible thing that Q has two meanings. It can be a prime power, or it can be a parameter in a Q expansion. So Fn of Q is the Q expansion of a modular form. And Fn of Q is periodic in n. I say roughly because there are a couple of other factors. There's a possibly fractional power of q, and there's a factor of q minus 1. But except for that, okay, it's sort of.
It's not polynomial periodic. It's not periodic means that it's periodic in the usual sense of n. And
So, I
it's
mean-
constant in each residue class, not a different polynomial.
It should be a constant. Well, okay. Yeah, no, you're right in a sense. So, okay, if I get rid of roughly, then what I should say is this times q minus 1 times q to some en over 24, and en is going to be an integer, which is periodic. So yes, your surmise is correct. Okay, so that's one kind of application I want to talk about. A second application I want to talk about goes back to work of Breuillard, Green-Guralnick, and oh, of course. Yes. Okay. And so what did they do? So they introduced the concept of a strongly dense. So according to these people, a strongly dense free subgroup of an algebraic group G, let's say over C, is a subgroup such that every non-abelian subgroup of gamma is Zariski-dense. I guess I should also say that gamma is free on more than one generator. I mean, yeah, this would be a trivial, right? So, yeah, so I want a non-abelian free subgroup, and it sits inside GFC. If the group as a whole is Zariski-dense, of course, that's just density. Strong density means every non-abelian subgroup is Zariski-dense. And they show that for every simple group G over C, there exists a strongly dense subgroup. And so I want to generalize that to Fuchsian groups. So the correct statement, I think, is the following. So if gamma is Fuchsian, and gamma is inside GOC, it is strongly dense. If and only if, same thing, every non-abelian subgroup is gamma is dense. Again, this is Zariski-dense. Though if you wanted to play a game like this, not with complex groups, but with compact groups, you could even talk about density in the usual sense. Okay, so this is, yeah, I mean, this.
So that's a stupid question. Gamma is an abstract Fuchsian group, and you embed it in some fancy algebraic group over C.
That's right.
So G is not SL2 or anything.
No. But that's not a stupid question. I mean, that's the sort of the key to the method is that gamma starts life with one representation, and you sort of want to leverage that representation to somehow construct these.
I mean, that's where you use its Fuchsian. I mean,
Yeah,
a lot of the stuff you might ask for, you know, one related group.
Yeah. And I think that's an interesting family of questions, and you know, not hopeless, but yes, that is why I want to focus on. Yeah. So the theorem. This is now a theorem of Breuillard and Guralnick. That if the AI are odd, are all odd, then for n sufficiently large, there is such a well, there is a strongly dense embedding of gamma in SLNC. So for large SLNs, assuming that these AIs are all odd, there does exist a strongly dense embedding. And I should say that the condition, it's an if and only if, because
It's clear that 3 is not large enough.
no, it's not clear that 3 isn't. I mean, it's clear that the method won't work for 3, but I don't know any results kind of going in the other direction. The only negative result I know is that if you had an even ni, then you'd have a point of order, you'd have an element of the group of order ni, so you'd have an element of the group of order 2. And if you take this element of order 2 and you conjugate it, you get another element of order 2, and you look at what 2 of them generate, they're going to generate something non-abelian, but it's no way it's going to be Zariski-dense in GC. It's going to be some kind of dihedral, maybe an infinite dihedral group. So we do need this condition, but it didn't turn enough to give the theorem. So that's what I want to use these results for. And now I want to say something about where the results come from.
And you have no idea how big that has to be.
I mean, I think I could prove that it works for 1 million. I can't prove it works for 3. I mean, it's not like a crazy number. It's not like doubly exponential. I think 1 million would be fine. Maybe if I worked hard, I could get it down to 10,000. But
1 million depending.
But it doesn't matter what
on the Fuchsian
the
group.
G and the AI are.
so, I mean, it matters, but it doesn't there would be a universal n that works for all. Yeah. I mean, the problem with all this stuff, let me just say, the problem with all this stuff is the possibility that the Euler characteristic can be close to 0. And if you don't allow elements of, the worst it could be if all the elements, all the AIs are odd, would be, I guess, a 3-3-5 triangle group. And that isn't that, the Euler characteristic is not that close to 0. I'll say more about that in a minute, but first I want to talk about the case which is easiest to understand, which is what happens if R is equal to 0. So gamma is just a surface group of genus G. And I want to begin with a theorem, which is due to make the same mistake twice. So there's a theorem of Rutinchuk, Benyash, Krivats, and Chernusov, 1996, which says that if we take Tom from SG to GLMC, this is an irreducible complex variety of dimension 2g minus 1 times n squared plus 1. Let me just say that the dimension is, I mean, it's complicated enough that it looks like there may be something subtle going on. There's nothing subtle going on. The point is you have two G generators in one relation. You have n squared degrees of freedom in GLM, so you would expect, well, you'd have 2g times n squared ways of sending those generators, but they have to satisfy one relation, so you'd think it would be 2g minus 1 times n squared. But you have to add 1 because the relation is a commutator relation, which means that you always get elements of SLN. So you shouldn't subtract off n squared, you should subtract off n squared minus 1. Okay, so that's why the dimension. I don't want to talk about errors.
Considering it up to conjugacy.
I'm not considering it up to conjugacy. I mean, I think that I think that these varieties are much more interesting when you consider them up to conjugacy, and probably one should think about what can be said. For example, you can say something about the homology of these varieties as well as this irreducibility, is the kind of methods I'm talking about. To what extent can you say something about the cohomology of the quotients by the G? I mean, I think that's a kind of an interesting question, which certainly should be thought about. Okay, so what I want to do is I want to describe a proof, not their proof, but proof which is due to Lindbeck and Shalev in 2005. And so what did they do? They said, well, let's look at count the number of homomorphisms from SG into GLN of FQ. So this is a special case of, counting the number of homomorphisms from SG to some, I don't know, call it H. It's not an algebraic group, it's a finite group. So if we want to count these homomorphisms, there's a formula which is due to Frobenius, which says the following. It's the number of elements in H, the power of 2 times the genus minus 1, times the sum over all irreducible characters of H of 1 over chi of 1 to the power of 2g minus 2.
Maybe it was Pierre's conference.
This is possible. Yes.
Could be
Right.
right. No, we're just having a side discussion.
Yes. Okay, so you can write down explicitly what the number of homomorphisms is. I mean, again, the sort of naive answer is you have 2G generators, so you'd expect H to the power of 2G, but you have one relation, so you'd expect H to the 2G minus 1, but there should be some correction term, and the correction depends on the characters, and so this is what you want to cover. And in this case where H is equal to GLN of FQ, then we can really do something with this. In the following way, we say, well, so what do the characters of GLN FQ look like? Well, I mean, there's a theorem of Green from the 1950s which characterizes them, but we know qualitatively that there are characters of degree 1. There are going to be Q minus 1 of them because they all factor through the determinant. You have Q minus 1 characters of degree 1. And then you have the other characters are all of fairly high degree. I mean, roughly speaking, Q to the power of n minus 1 is the minimum degree you're going to see once you get beyond degree 1. And if you think about the total number of characters, that's going to be the number of conjugacy classes, which is more or less the same as the number of characteristic polynomials, which is Q to the n. So if you have something with size Q to the n minus 1 and you're putting it at least the 2 power in the denominator, and the number of these things is Q to the n, this whole thing over here is going to be, in the case that we're interested in, is going to be O of 1, and usually little O of 1. So, what I want to say. I want to say that some chi in GLN of FQ characters of this, degree of chi of 1 greater than 1, of 1 over, already if I just took 1 out of chi 1 squared, this would be O of 1. And this power is at least as high as the second power. So we can, in terms of the asymptotic behavior, the main contribution to the asymptotic behavior is the Q minus 1 characters of degree 1. So roughly speaking, we could say that this thing over here, well, if we look AN equals of SG to GLN of FQ, so then AN is going to be asymptotic to number of elements in GLN of FQ to the power of G minus 1, 2G minus 1. Okay, so that's
Q is going to infinite.
I'm sorry?
This is Q going to infinite.
No. So, yeah.
In this analysis.
Yes. So if you, in the case, I'm sorry, yes, you're absolutely right. I sort of lost track of what I'm doing. I'm trying to prove something about the condition of this variety, right? How do you figure out what you're going to do?
Fixed now.
Yeah. In this case, absolutely. In this case, n is fixed and Q is going to infinity. Yes, thank you. The point is this. If you want to know about the variety HOM from SG to GLN-C, like you want to show it's irreducible, that's going to be the same thing as showing irreducibility in characteristic P when P is big. And so if you want to test that, then you want to count the number of points of large characteristics. You want to count the number of points of such this HOM. Maybe I shouldn't call it a variety because it may not be irreducible, but I want to count the number of points over FQ where Q is a power of large.
Pinchuk et al. Did not use this.
They did not use this, right. But if you do this, then you get a little more information than just the irreducibility. I mean, of course, you can see that you can see what happens here. I left out one factor. Of course, I just wrote down the H to the 2G minus 1, but I should also write down a factor of Q minus 1. So if you think about the asymptotics, when n is fixed and Q goes to infinity, you're getting n squared times 2G minus 1 plus 1. But we can say more because we know something about the size of this thing, which goes beyond the fact that it's asymptotic to Q to the n squared. So now let's say a little bit more precisely what this number is So if we count the number of elements in GLN of FQ, this is just Q to the n squared times the product as I goes from 1 to n of 1 minus 1 over Q to the I. So if you now shift perspectives and say, okay, instead of fixing n and sending Q to infinity, we're going to fix Q and send n to infinity, this thing is beginning to look very much like product I goes from 1 to infinity of 1 minus 1 over Q bi. And that looks very much like delta of 1 over Q, where delta is the Q expansion of, not delta, I shouldn't say, eta is what I should say. Yeah, where this is the Q, where I use eta, not like eta is usually written as a function of z. So by abusive notation, I'm writing it as if I'm just interested in its Q expansion. The only difference is a factor of Q to the 1 over 24. Right, so this is how modular forms, at least one way modular forms. Sure. At the end of the talk, I'll explain if there's another way. But before I do that, make sure that I've said, yeah, no, I want to say something. Okay, so that's the sort of asymptotics in N question. But I also want to say something about this Breuillard-Green-Guralnick-Tao question. So how does the irreducibility help us? So let me describe the strategy. Sort of goes back to, I think, Alon's comment. So gamma sort of starts out life inside PSL 2R.
But just sort of to be the way you sort of see that something is not reducible, is basically you would have number of irreducible components times Q to the dimension points in the limit, and that's how you see that it's irreducible.
Okay, so yes, I didn't say this and I should have said it. So let me say what you said, but a little bit more. So let's say that I have some I won't say variety because it may not be connected. Let's say I have some scheme of finite type over FQ, and I know something about the number of points over FQ. Maybe I know, for example, that the number of points over FQ to the n is Q to the n to the d power. Right? So I've got a variety X with scheme X, and X is equal to asymptotic. I suppose I know this. What do I actually learn about X? What I learn about X is that it has one irreducible component of dimension d, and any other irreducible components it may have are of lower dimension. So in principle, this kind of argument without any other explanation only proves that you get one irreducible component of the expected dimension, and maybe you've got smaller stuff. However, what is this? I really should have said this. This really was an omission. What is this variety we're talking about? It is the fiber of a morphism. Right, we've got a morphism from GLN to the power of 2G to, actually it's to SLN, because, which is given by x1, xg, y1, yg, maps to product of the commutators x by y. Okay, so we have a morphism of this kind, and our variety is the inverse image of 1 under this morphism. And because the dimension of, so that means all the fibers of this, so the minimum dimension of a component of a fiber of such a morphism is the difference of the dimensions here. And the difference of dimensions, so you don't actually have a possibility of a fiber of smaller dimension. And then by counting, we see we get the right number, is 1. Okay, now I wanted to, yes, so thank you for pointing that out. I meant to say that. Okay, so now I want to start off with this description over here where gamma sits inside PSL2 of R, and this condition of oddness of the AIs allows us to lift this embedding to a homomorphism from gamma to SL2R. So gamma now starts off life, if you will, sitting inside SL2R, and therefore sitting inside SL2C, and it's Zariski-dense as a subgroup of SL2C. And in fact, any non-abelian subgroup of gamma will still be Zariski-dense inside SL2C. And the reason is that we know what subgroups of Fuchsian groups look like, and if they're not essentially commutative, then they are not virtually solvable. And if you have a group which isn't virtually solvable sitting inside SL2C, it has to be Zariski-dense because no proper algebraic subgroup of SL2C is virtually solvable. Okay, so we know not only for gamma, but for any non-abelian subgroup of gamma that it's Zariski-dense in here. Now we take SL2C and we embed it in some way, in fact, in many ways, in GL2NC. We have many different embeddings.
But just to be clear, you never use I don't know what the definition of Fuchsian usually means discrete, that's irrelevant.
That actually is irrelevant for this part. I mean, we do use the presentation in calculating the number of points, but you're right. Okay, so we have all these, of course, they're a finite number. Basically, they correspond to partitions of n. We have all these different representations of SL2 inside GLN. And what we want to do with them is we want to think of them as giving different embeddings of gamma inside GLN. So you have a finite collection of these embeddings. And the philosophy is this: if we know that the space of representations is irreducible, then we have a single generic representation which specializes for all these different representations, right? And if I take the Zariski closure of gamma inside GLN under this embedding, well, it's going to be SL2, but it's going to be an SL2 embedded in GLN in a funny way. So we have all these different SL2s, and then we have the generic representation, whatever that is, and that has to, in some sense, specialize all these different subgroups. And so now there's some exercise, well, maybe more than an exercise, but there's something you have to say about algebraic groups, which is that if you have a group which in this sense specializes to this collection of subgroups, it has to be the whole group. I shouldn't say GLN, I should say SLN. It's really an SLN theorem, not a GLN theorem. Okay, so that's the idea of the proof. And this much, where we're just dealing with surface groups, is in a paper by the three of us, which actually has appeared in the Tietz memorial volume. But we didn't talk about Fuchsian groups with torsion, which is what I hope to get to today. Okay, so now I want to say something about how we handle torsion. I don't have a huge amount of time, so I'll be a little bit brief about this. So the crucial point is that this Frobenius theorem has a generalization, which is due to Hurwitz, and which says the following. So, okay, maybe before I write the theorem, I should say the following. Okay, we've got this gamma, and it has these classes Z1 through ZR, which are a finite order, okay, orders A1 through AR. And now we think about what happens if we have a homomorphism from gamma to some group H. And so, of course, what happens is that H has elements of order A1 through AR, or maybe, we could have a situation where maybe Z1 is of order, I don't know, order 15, and it maps to an element of order 5. I mean, something like that could happen. So you have to look at all integers dividing the AI and say, well, okay, you have conjugacy classes. You have an ordered R tuple of conjugacy classes inside H, where Z1 maps to something in C1 and ZR maps to something in CR. And we can partition the set of all homomorphisms from gamma to H according to which conjugacy classes the elements Z1 through ZR land in. And then we have a sum. So what we really need to count is the number of homomorphisms which send Z1 to C1, Z2 to C2, and so on. And that's what Hurwitz's theorem tells us. So let me write it down. You take homomorphisms, I'll write it this way. Homomorphisms, sort of restricted homomorphisms, are associated with C1 through CR from gamma to H. The number of elements in this set is equal to the following thing. It's equal to the product over I of the size of the conjugacy class times the number of elements in H, to the power of 2g minus 1 times the sum over characters here of chi of C1, chi of CR, divided by chi of 1, the power of 2g plus r minus 2. So that is the contribution of this R tuple to the total number of convex classes. So, I mean, again, this is if you ignore this correction term and just think about these terms, this is sort of what you would expect. I mean, you have the image of Z1 through ZR land in these sets. So the number of possibilities is given by this, and the X's and Y's, you have H to the 2G possibilities, and you have one relation in H. And so you would expect this, and this is the correction term. So that's Breuillard's formula. And of course, what we would like to do is we'd like to be able to estimate this. And what we'd like to say is we want only degree 1 characters to matter asymptotically. So this is a harder kind of question than before, because instead of just needing to understand the degrees of these characters, we also need to know something about character values. What we want, yeah.
Can you solve the conjugacy method or of the right order, the right orders?
Yes.
They agree with the AIs or the
Yes. So I mean, right, they have to be in the right order. So the order of CI must divide AI. Right, we don't, absolutely.
Yeah, okay.
Yeah. I mean, I think actually if you took CIs which didn't, that in fact this, I suspect what you would get from this formula is 0. So,
Then I suggest that you need to be a bit careful from this expression, right? It's not obviously about one model.
yes. Yes, that is it. So, yeah, so no, okay, no, I correct what I said. It's not that this would contribute 0. No, that is not true. Yeah, no, what is, the way that Hurwitz would have stated it is, if I have elements of these conjugacy classes and X's and Y's, the number of possibilities satisfying these equations is this. But it's not possible for me to, like, there are no homomorphisms. Like, there are no choices of row of Z1, row of ZR in C1 .CR. So this counts, I mean, this counts something, which is, it's going to be non-zero, but it's not counting anything which has to do with homomorphisms. Yeah, I mean, it's counting R tuples of potential elements here, but these elements aren't actual elements. I'm not saying this very well, but we can talk about it at the end if you want to. Okay, so this is a 50-minute talk. I mean, it's an hour talk. Oh, okay, then maybe I'm in slightly better shape than I thought. Okay, so what we want to do is we want to have some kind of control over these chi's, and ideally we would like control of the following kind. We'd like to know that we can bound chi of Ci above in terms of some power of chi of 1, because then we could hope to cancel all of these against this power and still have some positive power in the denominator, and so that would be the kind of easiest way of proceeding. Okay, and so there's a general theorem about this, which is joint work with Jeff, too, which says the following. It says that if I'm going to frame it for characters of classical groups. So if you want to think,
So H has to be sort of, need to know a lot about the representations of H. I mean,
in order to use this formula, you need to know a great deal about the representations of H, not just their degrees, but something about, yeah, that's right. So So this theorem concerns, H is a classical group. So the SLN, SPN, SON group of that kind, and G is an element, and chi is an irreducible character. And the absolute value of this is going to be bounded above by I of 1 to the power of 1 minus some constant times the support of G divided by M. So let me explain. So H is sitting inside GLN of FQ. And so G is an element that can be thought of as an n by n matrix. And what I mean by the support is it's the codimension of the largest eigenspace. So if you have a bunch of ones along the diagonal and just a little bit of stuff at the bottom, then you have, a small support. But most elements have support which is close to n. And C greater than 0 is a constant, but a very small one in our estimates. So this does give you, sort of qualitatively, an upper bound of the kind that you want. And for a lot of purposes, this would be good enough. But for this particular kind of application, we actually care what the exponent is, because we actually care that some of these exponents is going to end up being smaller than the denominator, and it usually won't be using this kind of estimate unless either R or G is quite big. G big is actually sort of trivial and is something that Liebig and Shalev understood well in 2005. But the case where G is 0 and R is big, R would have to be very, very big. It still gives new results, but it's not very strong numbers. So instead, we'll use a different result. So this is a theorem which is due to Zariski-Dense Liebig, Shalev, and Thiel. And it says the following. It says that chi of G is less than or equal to chi of 1 to the power of 1 minus the support of G divided by n. But there are a couple of little problems. So one is there's a constant C of n. And another property thing is that G is a split semi-simple element. So G is an element whose eigenvalues all lie in FQ. And there's a multiplier over here which depends on H is inside GLN of FQ. It depends on n, and it grows extremely rapidly with n. So if you're interested in asymptotics as n goes to infinity, this is a problem. On the other hand, what makes this result better than ours? What makes it better is we don't have this constant C over here. You get the constant 1, which is actually kind of the best you could hope for. So it has somehow the right asymptotics when n is fixed and everything else goes to infinity, but it's bad in how it behaves.
I think I've asked you this before, maybe in the last 20 years. Is this related to Howe's rank? These
Yes.
questions, it must be.
It is very much related to Howe's rank. In fact, that's what Tiep and I are working on right now, and I can tell you something about what we've done.
Especially for the simplicity.
But again, just a stupid question, the support of G, if I have a split civil element, it's just the maximum one n minus
The maximum multiplicity eigenvalue.
eigenvalue.
That's exactly it. So, okay. So using the Zariski-Dense result, this is joint work with Taylor, Jake Taylor, and Tiep. We can prove the following. We can prove that chi of G is less than or equal to chi of 1 to the power of 1 minus support of G over n, just what we want, plus some parameter which depends on Q for G non-unipotent. And epsilon of Q goes to 0 as Q goes to infinity. Okay, so let me just compare this to the Zariski-Dense result. The set of elements for which it applies is much larger, anything which isn't unipotent. So that's a good thing. And we've gotten rid of the constant over here, and that's a good thing. We replaced it with a constant here, which is not such a good thing. But at least if Q is large, this constant is small. And so since we're really interested in the overall size of this quantity, this is something we can live with as long as we don't want to look at very small values of Q. So that's the result that we end up using. Now, what can we prove with this?
What kind of result is this? What goes into such a proof?
So, yeah. So delightalistic theory certainly is the main ingredient. And
What gets rid of the constant in front of the n? How do you?
yeah, so I mean, basically what we do is we look at the proof of Besser-Kavnikov et al., which is a delightalistic proof. And we look at carefully at how big the things are rather than just saying, sort of like they weren't interested in this question, so they just sort of grouped everything together into a constant. So I think that's how to characterize it. Okay, so all right, so here's the theorem. So suppose that Q is greater than some Q0, which is an absolute constant, and chi of, not chi, the chi, okay, I'm using chi for two different things. The Euler characteristic of gamma is less than minus 1/6. So this says that, we can't do anything about the 237 group or even the 238 group. In fact, we can't do anything about 2,3n groups for any n, but except for those and a finite number of other small triangle groups, basically, maybe one quadrilateral group, we can prove the theorem. By the way, we can actually even deal with, there really are at most a finite number of exceptions to this, which we can write down, possible exceptions. We don't know if there are any real exceptions. But suppose all of this is true, then the asymptotics of gamma GLN Q are as predicted. That is to say, there is this periodic multiplier, which you multiply by Q to the power of 1 minus the Euler characteristic times n squared. And there's an interpretation of this periodic constant.
So now Q is fixed, n squared.
So now Q is fixed, bigger than some
Number, but
zero, n is going to infinity, gamma is fixed, and it's small. In that regime, we can prove this is true. Okay, so I think when I talked about
Now
it,
lower bound too, is that what you're saying?
so I guess you could think of it this way, that I have a lower bound as well, but I mean, it's, rather than thinking about it in terms of an upper bound and a lower bound, I would say I just have an asymptotic formula.
You can really compute.
I can, yeah,
Okay, yeah.
right. Now, how do you actually try to figure out the asymptotic formula, and how does that relate to, on the one hand, character estimates, and on the other hand, why are we getting modular form? Before we got a modular form for this reason, which had to do with the eta function. And this time we get a modular form for a totally different reason, which has to do with theta functions. And I want to spend a few minutes explaining where that comes from. So the fact that there are two different mechanisms for modular forms here, suggests that there's something conceptual going on that we don't understand. But anyway, that's not the point of view that we take. So the point of view we take is, suppose we have, let's say, A1 is equal to, let's say, 3, as an example. Okay, and we're interested in understanding this class C1 is a conjugacy class of order 3 in the GLN of Q. And to make life better for myself, I'm going to assume that Q is congruent to 1 mod 3, so that the cube roots of unity are actually in FQ. So this conjugacy class, what is the data that we need to specify to specify the conjugacy class? Well, of course, we need to specify the multiplicities of 1, omega, and omega squared as the eigenvalues. Right? We know that these 3 eigenvalues are going to add up to n. So we have, I don't know, call them M1, M omega, m omega squared, they add up to n. Now, we can think of these things, these triples, as forming a two-dimensional lattice. Well, I mean, we should translate this by this triple. Take m1 minus n over 3, m omega minus n over 3, and m omega squared minus n over 3. And so as we sum over C1, we're going to end up summing over lattice points. Now, which part of the lattice is contributing a lot to the sum? So the answer here is that when you think about, you're trying to count these things, you're multiplying by the size of the conjugacy class of C1 and by some other junk, C2, C3, and some characters. But mainly, you're interested in the size of the conjugacy class C1. When is the conjugacy class C1 biggest? Well, it's when the centralizer of this element is smallest. And when is the centralizer smallest? It's when all the eigenvalues are equal. So the main contribution comes from when these when this tuple is as close to 0 as possible. And you get smaller contributions as you work outward. And you're dealing with a sum over a lattice, and you figure out what it is you're summing over a lattice, and you see that it's exactly what you would expect if you wanted to get a theta function. Basically, you get a theta series. Now,
So theta usually means there's a quadratic somewhere.
there is a quadratic form, and where does that quadratic form come from? Well, basically, it comes from the following thing. What do we have when we have a conjugacy class? We have the size of GLN of Q divided by the size of the centralizer of this element, right? Representative of this. Now, what does the centralizer look like? Well, it's going to look like, this is going to be like GLN1 of Q times GLN2 of Q times GLN3 of Q, right? So now you see where the quadratic form is coming from. You have the dimension n1 squared plus n2 squared plus n3 squared, right? Q to that power. Yeah. So, okay, now to make this work, you have to be able to say that we can ignore.
Definite theta function?
It is a definite theta function, yes. We have to be able to say that we can ignore characters of degree greater than 1. And the problem is that the kind of estimates that I've been writing down depend on the support, and the support gets smaller, and therefore the estimates get worse when we move away from the center. And there are these two different things going on at the same time. On the one hand, when you're near when you move away from the center, the contribution of the product of conjugacy classes goes to 0 rather rapidly. But on the other hand, the character estimates decay rather badly. And so there's a question of whether, and that, strangely enough, it works fine as long as the Euler characteristic, you have a big enough gap between the Euler characteristic and 0. But I don't even know what to expect. Like with the 237 group, I don't know what actually happens. It looks to me like, in fact, the sum is dominated by things which aren't near the center, but which are in some band at some distance from the center. It's a very strange thing. And it may be that there really is a different phenomenon here. I don't know. But what certainly is true is that we have very good control of what happens near the center. And what that means is that when we have these well-balanced conjugacy classes, we can prove an irreducibility result for the homomorphisms, which send the ZIs to the well-balanced ZIs, just as we were able to do in the case of the surface group. Now, why do we care about that irreducibility result? Well, if we want to prove a result about strong density, it turns out that we only need to worry about well-balanced elements. We don't have to worry about elements which are badly balanced. Why? Well, because what happens how do we get representations from SL2 to SLN? Well, we get the
well-balanced, badly balanced elements.
Okay, I'm sorry. By well-balanced, I mean the multiplicities of the eigenvalues are all approximately the same. Yeah. So if I start off with SL2 and I have an element which has, let's say, eigenvalues omega and omega squared, and these are cube roots of unity, and I take representations in SLN, as long as I'm taking a representation is given by a partition, as long as the parts of the partition are large, like I'm taking symmetric powers of this, the eigenvalues will be well distributed. So as long as I limit myself to partitions which consist of a relatively small number of large pieces, I will have an irreducibility statement, and I'll be able to find many different representations of this kind, which all land in the same component. And therefore I will be able to use the specialization argument to show. So that's how the proof goes there. Sorry.
So I guess quite delicate theta function. I mean, you get theta functions and congruence groups if you choose orders cleverly.
Yeah. So, right, I mean, so if I understand what you're asking, like what happens?
Right, before it was just the eta function,
Right.
surface group. Now you've got this extra data, which is the AIs or whatever.
Right, you're going to have a product of eta functions, one for each conjugacy class. And it's even more complicated because I looked at what happened in the split case. If you're in the non-split case, and you still
Yes, before it was just 24.
then 24
Is not going to get worse than
it's not going to get worse than 24.
that.
I have a question about something mentioned at the beginning. So is it possible to study something like this for one-relator groups or?
So, I mean, I think it's a really interesting question. So what are the difficulties in trying to do something like this? So, I mean, one difficulty is like in the story, the way I'm telling it for these surface groups, we start off with a representation in SL2 and we can take symmetric powers of that representation. Now, if we have a one-relator group, how do we know that we start off with a representation? Do we know that there's a representation to SL2? I would expect that there normally would be.
When you say one-relator,
But
hyperbolic or not hyperbolic, it's someone not hyperbolic.
Okay, so there are several things I don't know how to do. So, and I don't know if hyperbolic helps you. Maybe it does help you in like a one-relator hyperbolic group. Maybe that helps you. So I don't know how to get an initial representation in SL2, which has the properties I want, which has, for example, the property that for any subgroup, any non-abelian subgroup is going to be dense in SL2. I want that property. The second thing I would want is I want to be able to count the number of homomorphisms from this group well, that should be okay. That part of the argument, well, I don't know whether it's okay, right? So I mean, I had this, yeah, I don't know whether that's okay. Like, I think you might be able to prove something like this, that for most relations, the number of homomorphisms from gamma with this relation to GLM and Q is about what you would expect. But I don't know how you would rule out the possibility of, for example, getting twice the number of I don't see any reason why it couldn't happen with gamma one-related group that the homomorphism from gamma to GLN has, two components. I don't see how you would prove that doesn't happen without something like this character formula for Hurwitz. So I don't know, like the algebraic geometry parts of the argument kind of, I think, work, but the character theory which gets it started, I don't know how to make that work. There is, of course, for any given word, there is some, you can do some harmonic analysis and analyze something about the number of homomorphisms from gamma to a finite group in terms of the characters, some properties of the characters, but whether it would have nice convergence properties that enable you to say, well, we can ignore everything except the degree one characters. So I don't know. I think it's an interesting question, but
in connection with that, Rapinchuk et al. Look at more general gammas like.
Yeah, that's.
They do.
Do they, in fact? I forgot.
Some representation variety dimensions that they.
Yeah,
that Breuillard quotes some of his work.
I think you're right. I did look at that paper, but it was a long time ago. I just don't remember. I think you may be right.
More questions? Michael, yeah.